this is 7.145. Here are the learning outcomes. At the end of this lesson, students should be able to define buffer solution. Next, write the Henderson-Hasselbalch equation for a given buffer solution. Are you ready? Let's start. Have you ever wondered, how does blood maintain a constant pH in contact with countless cellular acid-base reaction? The normal pH of blood is actually around 7.4. Do you know that severe illness or death can result from sustained variation just a few tenths of a pH unit from this normal value? Wow, that's a breaking news. There must be a system in our body to maintain the pH of the blood or any aqueous solution. What is it? It is called a buffer solution. What is a buffer solution? Buffer solution is a solution which has the ability to maintain its pH when a small amount of strong acid, usually represented as H+, or strong base, H-, is added to the solution. That means this solution is able to maintain its pH even though there is a small amount of strong acid or strong base is added to it. How does it happen? The solution must contain an acidic component so that it can react with the added OH. Added OH minus means added strong base. So that means the buffer solution first must contain the acidic component and also basic component, of course, because when there is the basic component, it can react with the added strong acid or represented as H3O, H2O+. That's the basic build-up of a buffer solution. So a buffer solution must consist of both acidic and also basic components so that it is able to react with the added strong acid or strong base. So you must note this. Next, the most common buffer components is made up of a weak base mixed with the conjugate acid pair from its salt. This is called the basic buffer. Another type of buffer is made up of weak acid plus its conjugate base pair from a salt. This is called the acidic buffer. Reminder, buffer solution must only contain either weak acid or weak base. If the system contains strong acid or base, the system cannot act as a buffer solution. Please take note. Right, before we go further, I need you to do this exercise. So you need to select which of the following are buffer systems. Select the answer. For A, KF/HF. So first you need to identify whether the acid is a strong or weak acid. So HF is a weak acid and F minus is the salt. F minus, the anion from the salt, is its conjugate base. Therefore, KFHF is a buffer solution. Good. Next, KBr/HBr. HBr, is it a weak acid? No, HBr is a strong acid. Therefore, KBr/HBr system is not a buffer solution. Next, we have this solution. What do you think? Is it a buffer solution? CO3 2- is a weak base and HCO3- is its conjugate acid. So it has a weak base and conjugate acid come from the salt. Therefore, it is a buffer solution. But since this is made up of base, this is a basic buffer. Easy, right? So let's move on. As I mentioned earlier, there are two types of buffer solution. The first one is the acidic buffer solution, in which the pH value is less than 7. And then the second one is the basic buffer solution, in which the pH is more than 7. For example, a weak acid and its conjugate base. This is the acidic buffer. For example, we have a mixture of ethanoic acid plus sodium ethanoate. The acidic component is of course the acid. Meanwhile, the basic component comes from the its conjugate base from the salt. Another example for the basic buffer is made up of a weak base and its conjugate acid. For example, mixture of ammonia and ammonium chloride. The acidic component is the ammonium chloride and ammonium ion NH4+, which is the conjugate acid for ammonia. And then the basic component is of course the ammonia. Right, when you are dealing with the buffer solution problem, first thing you need to know is to write down the equation involved in the buffer solution. Since there are two compounds, so you need to write down two equations. The first one is the dissociation equation for this weak acid. So weak acid dissociate means acid losing its proton, okay, then forming its anion here. But then since this is a weak acid dissociate partially, so please use the double headed arrow. And then we have a salt dissociate completely, so use the single headed arrow. So after the dissociation of the salt occur, that's mean way in the reacting vessel there are no more salt available. So can you guess what are the species left in the after we mix these two solution? What are the species left in the reacting vessel? Yes, we still have this bit of the acid as well as the conjugate base. Right, we also have the anion, which is the conjugate base of the weak acid that comes from the salt. Therefore, the buffer solution contains CH3COO minus and thus the buffer contains CH3COOH and CH3COO minus. This one is the acidic component. This one is the basic component. So we move on to the basic buffer. Basic buffer, for example, made up of ammonia and ammonium chloride. So first, we must write down the equation for the dissociation equation for ammonia. So ammonia react with water, dissociate partially. Since ammonia is a base, so base accept proton, so acid will lose its proton, forming OH minus. So this is the dissociation equation for ammonia. Next, we must write down the dissociation equation for ammonium chloride. This salt dissociate completely, right, into its cation and anion. So now, what are the species left in our reacting vessel? Is there any more salt? No. Yes. So what's left in our reacting vessel is ammonia and its conjugate acid. So ammonia from the basic component and conjugate acid from the acidic component. Remember, either it is an acidic buffer or basic buffer. Both type of buffer solution must exist acidic and basic components so that it can counteract with the strong acid or strong base that is added to it. Next, Henderson-Hasselbalch equation. What's the function of Henderson-Hasselbalch? It is used to calculate the pH of a buffer solution. It has two different formula, right? Two different equation for acidic buffer, and another one is for basic buffer. So first, we must write down the equation for the weak acid, and then write the Ka expression. Right, Ka equal to concentration product over reactant. We don't include the concentration of water because the concentration remains constant. Next, rearrange and take concentration H2O plus as a subject. Next, add negative log at both sides. Thus, pH equal to pKa plus log concentration of conjugate base. which is equal to the concentration of the salt, okay, over concentration of the weak acid. So you must memorize this equation. It will not be given in the exam, right? So you must remember this. This is the Henderson-Hasselbalch equation for the acidic buffer. Next, we are going to write down the Henderson-Hasselbalch equation for the basic buffer. The same step, first write down the equation for the weak base. And then you must write down the Kb expression. Rearrange and take concentration of OH minus as a subject. Add negative log at both sides. Thus, the equation of Henderson-Hasselbalch is POH equal to pKb plus log concentration of conjugate acid over weak concentration of weak base. So this concentration of conjugate acid is equal to the concentration of the salt. So if you are going to calculate the pH of the weak base, that means after using the Henderson-Hasselbalch, you will only get the pOH. So you must add on. So if you want to calculate pH plus pOH equal to 14. So that means after getting the value of pOH from the Henderson-Hasselbalch, pH equal to 14 minus the pOH value. Then you will only get your final answer. To conclude, here is the Henderson-Hasselbalch equation for the acidic buffer. Meanwhile, this is the Henderson-Hasselbalch equation for the basic buffer. Please have some time to memorize this because it will not be given in your exam. Next, we are going to do some example. Calculate the pH of a solution containing 0.2 molar CH3COH and 0.3 molar CH3COONA. Right, remember, first you must know that this is a buffer solution because it consists of weak acid. Okay, this is a weak acid and we have its conjugate base that come from the salt. So this is an acidic buffer. So when you are going to calculate the pH of an acidic buffer, that means you must use the Henderson-Hasselbalch equation. Substitute the value. Conjugate base here is this one, okay, the salt. Come from the salt. Then substitute the value, Ka given. And then concentration also given. Please make sure you substitute the correct value here. Then you will get the answer. The pH of the acidic buffer is around 4.9 into. Remember, you must get less than 7 because it is an acidic buffer. Next, this is an example of a basic buffer. We have ammonia and its conjugate acid. Must calculate the pH, so must use the Henderson-Hasselbalch equation. Okay. Substitute the value. Since this is just pOH value, this is not your final answer. Remember, this is the relationship between pH and pOH. Therefore, you must minus the value. You must subtract the value pH you get earlier. And then end up, you will get the value of the pH for this basic buffer is around 9.36. So, pH for a basic buffer must be more than 7. So, before we end the lecture, please scan the QR code to exit ticket. Thank you for watching. Bye.